A game is played in which each throw of a ball lands in one of two holes, the closer hole or the farther hole. A throw landing in the closer hole scores 2 points, while a throw landing in the farther hole scores 5 points. Player's score is equal to the sum of the scores on their throws. Jasmine has 3 throws that each scored 2 points and 4 throws that each scored 5 points. What is Jasmine's total score? So that would be 2 times the 3 throws plus 4 times the 5, and that totals 26. Sam had twice as many throws that scored 2 points as throws that scored 5 points. If Sam's total score was 36, how many throws did Sam take? So 2x represents the number of throws that scored 2 points, so 2 points for each. And x represents the number of throws that only scored 5 points or scored 5 points. So there you go, and we know that that's equal to 36. So this is going to be 4x plus 5x, so that's 9x is 36. And therefore x would be equal to 4. So 4 represents the number of throws that scored 5 points, and therefore the number of throws that scored 2 points would be 2x, which is 8, and so therefore the total number of throws would be the 4 plus the 8, which is 12. Tia had T throws and each scored 2 points, and F throws that scored 5 points. If Tia's total score was 37, determine all possible ordered pairs TF. All right, so that basically means that we have 2F plus 5T, and that's equal to 37. Or I think I mixed this up. I think it should be 2T plus 5F. Yeah, I gotta make sure I do it the right way. Okay, so basically what we have to do is find integer solutions to this equation. So let's make a little table, T and F, and let's see. If T is 1, then F will be 7. You guys can do this math, fairly straightforward. And the next time we get an integer is when T is 6. That makes this 5, 11, 3, and 16 and 1. So those are the only integer solutions to that equation, and those would be the ordered pairs. And finally, we have the game is changed so that each throw is going to be 6 or 21 points instead of 2 and 5. Explain whether or not it is possible to have a total of 182 points. So this time, let's say we have X throws and each of them scores 6, and then we have Y throws where each of them scores 21. And that would equal the total. Now they're asking, is this possible? Well, I don't know. Let's see. The only thing I could think of is like if you factor out a 3 on this side, you get 2x plus 7y. And if you factor out a 3 on this side, you can't, because 182 is not divisible by 3. So basically what this means is, like, since everything's an integer, this would have to be, since this is divisible by 3, or this is a factor of 3, a multiple of 3, this would have to also be a multiple of 3, and it's not if you're, talking about integers. So therefore you can explain that in a sentence that since this side is a multiple of 3 and this side is not, this would not be possible. In each question below, ABCD is a rectangle with AB equal to 2, AD equal to 15. Point E is on BC. What is the total area of the shaded region? So total area of the shaded region, I believe, would be the total area of the rectangle, which is 2 times 15, minus the area of that triangle AED. And that triangle would be 1/2 base times height, where the base is 15 and the height is 2. So this looks to me like 30 minus 15, and that is equal to 15. Point F is on BC, and BD intersects AEF at G. If the area of FGD is 5, what is the area of the shaded region? So FGD, that is 5 right there. Okay, so where do I go from here? FAD, I think I can figure that out FAD is 1/2 base times height. The base would be 15 and the height would be 2. So that'd be 15. So that means that GAD would be 15 minus 5. So that's going to be 10 in there. Is that right? Yeah, I think so. And therefore, if we just figure out BAD, and BAD would be, again, 1/2 base times height, which is 15 times 2, and that's 15. And therefore, BAG, which is the shaded region, would be 15 minus 10, which is equal to 5. And the last one, point P is on BC, R is on AD, BR and AP intersect at S, and PD and RC intersect at Q. If PQRS is 6, determine the total area of the shaded regions. Okay, so let's put that 6 in there. Okay, so the first thing I'm going to do is the triangle PAD. That, I believe, would be 1/2 base times height, where again the base is 15 and the height is 2, so that's 15. So let's label this. I'm going to call this shaded region 1, this shaded region 2, this shaded region 3, and this shaded region 4. So what we essentially want is 1 plus 2 plus 3 plus 4, the areas. Well, if PAD is 15, then we know that part of it is 6, so we can conclude that this 1 and 2 would be 15 minus 6, which is 9. Right? And very similarly, BRC, that area, would be, again, 1/2 base times height, 15 times 2, which is 15. And if you subtract the 6 from that, you would get these guys. So it would be 15 minus 6, which again is 9. So this whole thing would be 9 plus 9, which is equal to 18. For any positive integer with 3 or more different non-zero digits, let the cousins be defined as the result of switching 2 digits of the integer. For example, 156, I should say, has 3 cousins, 516, 651, and 165. In no particular order, 5 of the 6 cousins of 6, 2, 3, 8 are listed below. Which cousin is missing? Okay, so I guess we do the switcheroo. If we switch 6 and 2, we would get 2, 6, 3, 8 on this parent number, I guess. If we switched the 6 and the 3, we would get 3, 2, 6, 8. If we switched the 6 and the 8, we would get 8, 2, 3, 6. 8, 2, 3, 6. If we switch the 2 and the 3, we would get 6, 3, 2, 8. If we switch the 2 and the 8, we would get 6, 8, 3, 2. And finally, the 3 and the 8, if those were switched, you get 6, 2, 8, 3. So I guess all of them are represented, except which one's missing here? I think the 6, 8, 3, 2. This one is not there. So that's the one that's missing from the list. In no particular order, the following list contains an original integer as well as its cousins. What is the original integer? Okay, what is the original integer? All right, interesting. Well, how do I do this here? It's 6 digits, right? Okay, 6 digits. And I don't know what the original integer is, but let's say it's A, B, C, D, E, F, meaning those are the representing the digits. Now, if we were to make a switch just with A, if you do the first switch, A and B, it would be A and B like that. And then if we switched A and C, it would be A and C like this. And the rest of these would be the same. B, D, E, F. You see what I'm doing? I'm just going to switch the A's and then see what happens. A and D would switch and then make that. And then A and E would switch and make that. B, C, D, F. And then finally, if we switch the A and the F, the A would go here, the F would go here, and you have B, C, D, E. Okay, so what does that show me? That shows me that these are involved with the A. So you would have 5, if you do the switch, you'd have 5 numbers that do not have the A as the first digit. Now, how many cousins are there? There'd be some original number, and the rest would be cousins. So there'd be 15 cousins. So that means if there's 15 cousins, 5 of them do not have A as the first digit, but the other ones will. So 10 would have A as the first digit. Yeah. So we have to look at these numbers and see, does some number appear 10 times as the first digit? Let's see here. The 7 appears 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But you gotta remember there's 16. I don't know which one is the first. I don't know which one is the original integer. That's why I've sort of overcounted. But I think that's pretty convincing, because the 2 only, the 2 only appears once, and 1 only appears once. So I'm pretty confident that the 7 would be the first digit. So whatever the number is, yeah. And then similarly, you would do the same thing where the nth digit of the original integer is the integer that occurs most frequently as the nth digit in the given list. So let me write that out. So as previously said, the nth digit of the original integer is the integer that occurs most frequently as the nth digit of the given list of cousins. So for example, the first digit of the original integer occurs most frequently as the first digit in the given list of cousins. So we saw what is the most common first digit, and that's a 7. So that's got to be the first digit of the given number. Now, what's the most common second digit? I'll let you go through this list and you'll see that it's 2. So 2 has to be the second digit of the original integer. Apply the same principle. And then go through the list. What's the third most common digit? That's a 6. So that's got to be the third digit of the original integer. Then which number is the most common fourth digit in this list? And that would be 4. So that's the fourth digit of the original integer. What number is the most common fifth digit in this list? And that's a 9. So 9 is the fifth digit of the original number. And finally, 1 would round it out. So if you follow this principle right here, and this was the explanation right here, you will get this as the original. And 726,491 is somewhere in here. Yeah, here it is, 726,491. This is the original. Suppose that C and D are distinct non-zero digits. The 3-digit integer CD3 minus one of its cousins is equal to the 3-digit integer D95. Determine the values of C and D and show that no other values are possible. All right. So we have a situation where we have C, D, and 3, and we're going to subtract from it. So subtract from it one of its cousins. So the cousins are either DC3, 3DC, or C3D, right? And only, looks like minus 1. Okay, so only one of these work. The other ones don't work. Okay. All right, so let's take this one step at a time. Let's do the CD3 minus DC3. Let's see what that does. Well, immediately, I don't know what C and D are, but since the units digits are the same, this is going to end in a 0. And if it ends in a 0, it cannot be equal to this D95 because that ends in a 5. So right off the bat, this one is out. So let's try the next one. We have CD3 minus 3DC, okay. We got a problem here because we got numbers and letters, so we got to convert these. So C, that's 100C if you convert this C, and then that's 10D plus 3, and then we're going to have to minus 300 minus 10D, and minus c, like that. I think that's correct. I think. Let me just double check what I did here. Yeah. Okay, so where do I go from here? Well, one thing I noticed is that we want to get this guy, right? So if I do CD3 minus 3DC, the units digits are going to go from 3 to 5. And that's going to happen if C is equal to 8. Yeah. Right? That would make sense because 3 minus 8 would bring it back to like 5. So I'm confident that's 8. So that's going to be 8D3 minus 3D8. So this makes it a little bit simpler. So this will be 800 plus 10D plus 3 minus 300 minus 10D minus 8. So the D's cancel, so we're left with 500 minus 5, and that's 495. So that is 495, and therefore the D is equal to 4. Yeah, I think that's it. I think I solved it. So C is equal to 8 and D is equal to 4. And this one here, that won't work, and I will let you figure that out, or I can do it here really quickly. CD3 minus C3D. Okay, so we're going to have 100C plus 10D plus 3 minus 100C minus 30 minus D. So the 100C's cancel. This becomes 9D minus 27. And I think this, D is a digit, right? So even if D was the maximum digit, which is 9, this will actually be a 2-digit number. Yeah, 2-digit number. So it's not going to be a D95 type situation. So, all right, we proved it. Suppose that M and N are distinct non-zero digits. The sum of the 6 cousins of the 4-digit integer mn97 is equal to the 5-digit integer nm7. Determine the values of m and n and show that there are no other values possible. Okay, well, first of all, what is the parent nm, nm, and 7? Okay, so let's list the cousins. The cousins would be nm9. Hold on. What are we doing here? The original number is not this. That's the sum. Oh, yeah, that's the sum. This is the original. Okay. Got a little ahead of myself. Okay, so now let's list the cousins of this guy. So that'll be nm97, 9nm7, 7n9m, m9n7, m79n, and mn79. So these are the cousins. Now we got to add these, right? Because they want a sum. Yeah, the sum. Okay. Oh boy. Gotta add all these guys. Okay, so this will be, I'm going to just do it quickly because the 1,000 will be the end there, the 9 here, the 7 here, the m here, the m here, and the m here. See what I did? I'm just adding the thousands. And then the hundreds would be m 3n plus 16. I just did that. This m, these 3 n's, and the 16. And then 10, similarly, I think that's going to be 27 plus 34 plus m plus n. And then finally, the ones digit looks to me like 21, 30 plus m plus n. Okay. Now, does that help in any way? Where do we go from here? All right, let me think about this here. Okay, they gave us the sum. Okay, that's helpful a little bit. They're telling us that sum of the 6 cousins is this guy. So it's nm, nm7. So if you were to add up these 6 guys, which is what I did, it would be nm, nm7. So this is the units digit, so that adds up to 7. Okay. How does that help? So that means 30 plus m plus n has a units digit of 7. That means that either m plus n is 7 or m plus n is 17. Because if they were both 9, are they distinct? Yeah, they're distinct. So I think the highest m plus n could be was 9 plus 8, which is 17. Okay, so from these scenarios, we would get only a finite number of possibilities. 1, 2, 3, 4, 5, 6, 7. I think 7. You'd get either 1, 6 for m and n. I'm going to have to make a little table here. 2, 5, 3, 4, 4, 3, 5, 2, 6, 1, 8, 9, or 9, 8. Okay, and then we just got to go back and substitute these numbers into this guy right here. That one right there. And when you do, I mean, I'll let you guys do the math. For the first one, the sum, if you crunch and put all the numbers, it'll be 2, 8, 9, 4, 7. And then this one, that's fairly straightforward, right? That's going to just be 6, 1, 6, 1, 7. Yeah. Well, we want to have a situation where these two numbers match, because the sum has to be equal to this. And in this case, it doesn't, so that's no good. And then similarly, go through each of these and do all of them. When you get to this one, you'll find that the sum is 3, 4, 3, 4, 7. And the number NM7 is also 3, 4, 3, 4, 7. And this is the only one that actually works. So that's the only possible values of m and n for which all of this works out. The Great Math Company has a random integer generator which produces a number from 1 to 9 inclusive, where each integer is generated with equal probability. Each member of the multiplication team uses this generator a certain number of times and then calculates the product of their integers. Amarpreet uses the generator 3 times. What is the probability that the product is a prime number? So if you're using the generator 3 times and it's given 3 different numbers, the only way you can get a prime number is if you have 1, 1, and the prime. Or you can have a situation where the prime number is chosen second, or generated second, I should say, or generated first. That's the only way that the overall product will be the prime. Okay, so let's figure out the probability. For any probability, the denominator will be the maximum number of choices. So since we can generate 1 to 9, there's 9 choices for the first number, 9 choices for the second number, 9 choices for the third number. So probability would be 9 times 9 times 9, which is 9 cubed. Yeah. Okay, now let's figure out the probability of getting a 1 and a 1 and a p. The probability of getting a 1, well, not probability, sorry. The number of ways to put a 1, there's only one way, just the 1. Here there's only 1. But how many ways can we put a prime number? Well, between 1 and 9, how many prime numbers are there? Well, if I remember, 1 is not prime, 2 is, 3 is, 5 is, and 7 is. So 4 choices for that. So 1 times 1 times 4 is 4. So you have 4 ways of doing it, 4 ways of doing that, 4 ways of doing that. So a total of 12. So 12 over 9 to the power of 3. And this is 12 over, what is it, 729? And I think you can divide through by 3 and you get 4 over 243. So that would be the probability. And moving right along, Braxton uses the generator 4 times to determine the probability that the product is divisible by 5, but not divisible by 7. Okay, so 4 times 1, 2, 3, 4. And I think we have 4 scenarios here. Remember, they're multiplying these numbers. Okay, so if we want the product to be divisible by 5, if there's a 5 in there, that will be sufficient. So you can have all of them as 5s, and that would definitely be divisible by 5, right? 5 times 5 times 5 times 5, whatever. And there's only one way of doing that. If all the digits selected were 5s. Yeah, there's only one way of doing that. Or you could have 3 of them as 5s, and then this one is anything from 1 to 9 except a 5. So that means from these 4, 1, 2, 3, 4, you choose 1 for this guy, and yeah, you choose 1. Or actually, wait, I think it's better to do as from the 4 numbers, choose 3 to be the 5s. Yeah. And then for this guy, you have how many choices? It cannot be a 5 and it cannot be a 7, because you do not want it divisible by 7, and you only want 3 5s in this. So there's 7 choices remaining. So 4 choose 3 is what? 4? And then 4 times 7, so that's 28 choices there. For 2 5s, from 4 choose 2 for the 5s, and then for each of these guys, you have 7 choices, so 7 times 7. Well, the same logic as before. So 4 choose 2, I believe, is 6, and then 6 times 49, so it's going to be 294, I believe. And then finally, you have only 1 5. So from the 4, you choose 1 for the 5, and then you have 7 times 7 times 7 for the other 3 choices. So that's going to be 1372. So if you add up all these guys, you would get 1695. And then, of course, it's over 9 to the power of 4 this time, because there's 4 choices, and the maximum number of choices for each is 9. And this is 1695 over 6561. And in lowest terms, I think that's 565 over 2187. Camille uses the generator 2023 times. Let P be the probability that the product is not divisible by 6. Determine the ones digit of the integer equal to P times 9 to the power of 2023. So this time we have a lot of numbers. Obviously, I'm not going to be able to write out all the spots, but there's 2023 of these numbers. And therefore, for each, you have 9 maximum choices, correct? So when you figure out the probability, it's going to be something over 9 to the power of 2023. And then, of course, what they're doing is whatever this number is, they're just isolating for it to give this P times 9 to the power of 2023. And then they're saying, what's the units digit of that? Okay, so let's see what we can get. Okay, so it is not divisible by 6. All right, so not divisible by 6. So if it's not divisible by 6, there obviously can't be a 6 anywhere in here. So we can't have a 6. We also cannot have a product of 2 times 3, because that would give you a 6. Because, for example, if one of these numbers was a 2 and another one was a 3, then that would be divisible. The entire product would be divisible by 6, and we can't have that. So we can't have a 2 or any multiple of 2, 4, or an 8. And we also cannot have a 3 or any multiple of 3, which would be 9, between the numbers 1 and 9. Okay, so we've got a few scenarios here. The first scenario is, well, we can't have a 6 at all in any scenario. If we also cannot have these guys. But we could have one, like you could have like a 3, but if you don't have a 2 or a multiple of 2, it would still be okay. Or you could have a 2 or a multiple of 2, but you can't have a multiple of 3. So I hope that makes sense. Okay, so let's work with this now. Okay, so let's start off with this guy here. That one, since, whoa, we can't have any of these. You can't have 6, 2, 4, 8, or 3, 9. So the only numbers that are left are 1, 3, and 7, right? 1, 5, and 7, I believe, is the only numbers that are left that we can use. So if we have all these numbers, you know, that go on all the way till 2023 of these numbers, for each of these we have 3 choices, either a 1, a 5, or a 7. So therefore the total number of choices would be 3 to the power of 2023. Yeah. Okay, we took care of that one. Now let's take care of the next one. If the next one, you can not have a 6, you can't have a 2, 4, 8, but you can have a 3 or a 9. So now the numbers we can have are 1, 3, 5, 7, and 9. So very similarly, now we've got a scenario where in each number we have 5 possibilities. So therefore we have 5 possibilities here, 5 possibilities there, and so on. So the total would be 5 to the power of 2023. But we have overcounted because all the ones that are 157 are also going to be included here. So we have to subtract from this number the ones that we already counted here. So this would be the total for that guy. Yeah, because of the overcounts. Okay, so now we're down to this guy. That scenario, we are only allowed to have 2, 4, 8. We can't have 6, 3, or 9. So what numbers are left? 1, 2, 4, 5, 7, and 8. Yeah, we're not allowed to have the 6, 3, or 9. So we have 6 numbers this time. So by the same logic as before, we can have 6 numbers for each of these. So it would be 6 to the power of 2023. And is there any overcounts here? Yeah, the 157, because this has 157, this has 157. So we have to subtract from that this 3 to the power of 2023. Okay, and I think that's it. So now we have to add these guys. Add this guy, this guy, and this guy. When you do, you get 6 to the power of 2023 plus 5 to the power of 2023 minus 3 to the power of 2023. And we have to figure out the units digit of that. Yeah. Okay. How do we figure out the units digit of that? All right, well, 6, if we just concentrate this one at a time. Any power of 6, 6 times 6 times 6, I think has a units digit of 6. Yeah, every power of 6. I'm pretty sure about that. Similarly, any power of 5 would have a units digit of 5. 5 times 5 times 5. But 3, it's not that simple. So we have to look for a pattern. And I'm sure some of you guys have done this in the past, like this. So let's look at the powers of 3. This is 3, this is 9, this is 27, this is 81. And you'll see that when you do these guys, there should be some sort of pattern, hopefully. Well, 3 to the power of 5 and so on, we will do and see. We got 243, and then we got 729, and then we got 2187, and then we have 6561. So do you see a pattern? This is 3971, right? If you just look at the units digits, this is also 3971. So that means it's 3971, 3971, so on. So let's just say every multiple of 4 would have a units digit of 1 when the exponent. Is this a multiple of 4? I don't think so. Well, let me do it somewhere else here. 3 multiple of 4 would be, I think, 2020. And that would have a units digit of 1. And then 3 20 21, 3 20 22, and 3 20 23. Those would follow. Then we'd go back to 3 9 7. So 3 9 and 7, like that. So 32023 would have a units digit of 7. Okay. So now we got the units digits. Let's do this math. That would be 11 minus 7 is 4. And there you go. So that is the answer to this question.